Now that we've derived the kinematic equations, I want to give you an idea as to how we might go about using them for problems. So just to give you some examples, things that you'll see in your homework and assessments. So let's start with this problem right here. An object starts from rest and maintains an acceleration of 7.0 meters per second squared for a time of 1.3 seconds. We're trying to figure out the final velocity and the displacement of this object. Now there are going to be multiple ways to do these types of problems. I'll show you that on this first problem, but if you go about a problem a separate way than your classmate or than I did, and you end up with the same answer, there's no reason to be alarmed. Like I said, there are multiple ways that will work on these. What I find most convenient to do, however, to start, regardless of how you end up finishing, is to identify your givens. What are the things that are given in the problem? So in this case, I see a couple of givens right off the bat. I see that the time is 1.3 seconds. I see that the acceleration is 7.0 meters per second squared. But when you're doing these kinematic equations, most of the time you've got to have three givens in order to do anything. So there's actually a hidden given here, something I'll end up calling a hidden given. And that's this right here. The object starts from rest. So from that we can say that the initial velocity is equal to 0. Now we've got our three givens. Let's determine the final velocity of this object here. So I'm going to use one of our first kinematic equations, and that's this guy right here. Final velocity equals initial velocity plus acceleration times time. All I need to do here is plug in my givens. My initial velocity is 0. I wouldn't really even need to write that. Plus acceleration times time. And what you'll find here is that the velocity is 9.1. Now you know that because you're talking about velocity and because this is physics class, you're probably going to have units of meters per second here. And that is true. If you're not convinced of that, you could go back and look at the units of our math, and you can see that acceleration is meters per second squared, time is in seconds, so there'll be a second that cancels top and bottom, and you will indeed be left with meters per second. Now if we're going to try and find the displacement, like I said, there are multiple ways that you can do this. Let me just show you a few of the ways that you could do this. So in order to find the displacement, we could use another one of our kinematic equations, this guy right here. And if I plug in my givens, the initial velocity is 0, so once again, I really wouldn't even have to write this part over here. This whole thing is just going to go away. Anything times 0 is 0. And when you do this, you will get a displacement of 5.9 meters. Now, like I said, you might choose a different way to go about this problem, and that is completely okay. For example, you might choose to use the following equation. You might choose to say that final velocity squared equals initial velocity squared plus 2 times acceleration times delta x, another one of our kinematic equations. Completely legitimate. You can take your givens and throw it in here. So we had a final velocity of 9.1 meters per second. We figured that out earlier. The initial velocity was just 0, so it doesn't matter that we're going to square it. I'll show it anyways. Our acceleration was 7.0. You can check from above, and we're trying to solve for the delta x. So what you'll end up with then, 9.1 squared. 2 times 7.0 is just 14, so I'll divide both sides by that to get a delta x that, once again, is equal to 5.9 meters. Of course, you can also get a little bit tricky and use one of the equations that we looked at in the last video, and that's that displacement is equal to average velocity times time. And if we plug in that tricky form of average velocity that we were dealing with earlier, and plug in the things we know, initial velocity was just 0, final velocity was 9.1 meters per second, and the time was given as 1.3 seconds, you'll still get 5.9 meters. Many, many, many ways to do these problems. Let's look at another one. An object starts from rest, there's another hidden given right there, and maintains an acceleration of 7.0 meters per second squared, the same acceleration as last time. Now, if I want to know how long it will take the object to go 91 meters, there's another given right there, and I'm also looking for the final velocity. So let's identify those givens. We've got starts from rest. Initial velocity is equal to 0. We know that the acceleration is 7.0 meters per second squared, and that we're wanting it to go 91 meters. That's a displacement. That's a change in position. So we're looking for a couple things. We're looking for time, and we're also looking for the final velocity. Once again, many ways that you can go about doing this. This will just represent one of the ways that you could potentially solve this problem. So here's one of our kinematic equations right here. Bf squared equals bi squared plus 2a delta x. And let's plug in the things that we know. So I'm going to solve for final velocity here. My initial velocity was just 0. It doesn't matter if I square that. I'll show it to you anyways. 2 times the acceleration was 7.0 times the displacement we were looking for was 91. If you plug this all in your calculator, you'll see that final velocity squared is equal to 1,274. And then to find final velocity, then you would just need to square root everything. So when you do that, you will find a final velocity of 36.7. And you know that your units of velocity will be meters per second. Now, if you wanted to continue along and find the time, like I said, many ways to do that. I'm just going to show you one of them. You could do that with the following equation. We just figured out that our final velocity was 36.7. May as well use it. Our initial velocity was 0. I wouldn't have to write that. Acceleration of 7.0. And our time is what we're looking for. So if you solve for time, divide both sides rather by 7.0, that should be equal to time. And when you do that, you'll find that time is equal to 5.1 seconds. Once again, you could get the units from the math, but you know that time is going to be in seconds because, after all, this is physics class. We'll do more examples like this in class, but that's a good start.